Hello everyone. This is part 3 of section 14.9 Lagrange multipliers. Just one last example here, but before we get to the example, little concept. If we want to find the points on a graph that are closest to a given point, we're going to have to minimize the square of the distance between those 2 points. So given some point, x sub 0, y sub 0, z sub 0, the square of the distance to another point is given by our distance formula. So typically, it's the square root of the difference between the coordinates, each of the coordinates squared, but since we're squaring both sides, that gives us d squared, which minimizes the square of the distance, or minimizes the distance. So find the minimum distance from this point to this plane. Basically, if you think about the idea, we have some plane here. This is the x plus y plus z equaling 1 plane. And you have a point. Our point is 2, 0, 0. And we want to minimize the distance. So we're saying that there's any point here, x, y, z, but the point we're looking for is really this point, which minimizes the distance, so it'd be perpendicular to the plane. To that point would be the minimum distance. So our primary or objective equation is our equation here, the square of the distance. So we'll say d squared of x, y, z is, okay, let's use the point as x sub 0, y sub 0, z sub 0. So we'll have x minus x sub 0 is 2, quantity squared, plus y minus y sub 0, 0 squared, plus z minus z sub 0, 0 as well squared. And so therefore the square of the distance is x minus 2 quantity squared plus y squared plus z squared. So that's our primary. That's we want to minimize this. Okay, so then we get our secondary or constraint. And that basically is the plane. So x plus y plus z is 1. So if we say g of x, y, z then is x plus y plus z minus 1, and we take, say, just to be consistent with our notation, f of x, y, z to be the square of the distance. X minus 2 squared plus y squared plus z squared. Excuse me. Okay, so now form our uppercase F function, which is a function of x, y, z, and lambda. So that's going to be the f of x, y, z minus lambda times g of x, y, z. Okay, so we have x minus 2 quantity squared plus y squared plus z squared minus lambda times the quantity x plus y plus z minus 1. Okay, so now the partials. So partial with respect to x. Okay, here we have to actually, you could have expanded this if you wanted to, but using the general power chain rule, u to the n, whatever you want to think of it as, bring down the 2 times that same function, x minus 2, power 1 less would be 1, and then the derivative of the inside is 1, so there's no real need to write it. And then the derivative of the y squared and z squared are both 0, and then we'll have minus lambda, because the derivative of x is 1, and the derivative of all these guys are 0. So that's f sub x, f sub y, the partial with respect to y, 2y, because the x and z's are constants, minus lambda. And then the partial with respect to z is 2z minus lambda, and the partial with respect to lambda is x plus y plus z minus 1. Okay, so now we need to solve the systems by first setting these equal to 0. So let's say 2, I'm going to choose to distribute the 2 at this point. So 2x minus 4 minus lambda is 0. 2y minus lambda is 0. 2z minus lambda is 0. And then x plus y plus z minus 1. Actually, I'm sorry. That's a mistake. These should all be negative, right? Let me fix that. I apologize. So it should be a negative. X minus y minus z plus 1. Now set equal to 0. Okay, so we'll solve for our lambdas here. So 2x minus 4 would be lambda. Here lambda is 2y. Lambda is 2z. We'll hold off on this. And let's see, if I take these two guys, 2y equals 2z, so y is equal to z. Let's see what I want to do here. Okay, so I think what I'll do, you could solve this system any way you like, but I'm going to take the x and the y now. Both are equal to lambda, so I could say 2x minus 4 is 2y, and then divide by 2, so y would be x minus 2. And here I have y in terms of z, so actually, I know I'm going to have to come back to this equation. And let me see, I think it'd be advantageous to just say that solve this for x in terms of y. X would be y plus 2. Because now what we could do is consider, use the f sub lambda equal to 0, which was the negative x minus y minus z plus 1, and replace everything to be in terms of y. So minus y plus 2 is quantity, minus y minus z is y, plus 1, okay, that was equal to 0, because again I was coming from the partial with respect to lambda equation. So let's see what we get here, minus 3y, and that'd be minus 2 plus 1, minus 1 is 0, so minus 3y is 1, and y is negative 1/3. So if y is negative 1/3, then z is also negative 1/3 because z was equal to y, and then x was y plus 2. So therefore x is equal to minus 1/3 plus 2, which would be 5/3. So the point that we're talking about is 5/3, negative 1/3, and negative 1/3. And notice that that's on the plane because x plus y plus z is equal to 1. And if you wanted to find the distance, because we're going to minimize the distance, we want to know what that distance is, we'll take the p sub 0 to be 2, 0, 0, and p1 to be what we found, 5/3, negative 1/3, negative 1/3, and then the distance is the square root of the difference between the coordinates squared. So let's say 5/3 minus 2 quantity squared plus a negative 1/3 minus 0 squared plus again a negative 1/3 minus 0 quantity squared. And so let's see what that gives us. This would be a minus 1/3 squared would be 1/9. Just get a 1/9 here and a 1/9 here. So square root of 3/9, or radical 3/3. Okay, so that's it for Lagrange multipliers, and this is actually the end of the material for exam 3. So check your messages in Blackboard as well as your T-Wolves email. I'm going to have a review sheet and try to decide exactly how we're going to deliver this exam. So check your emails and your Blackboard announcements once again.